Yeah, I'm Anton Lorenzen. I finished my master's at the University of Bonn. Just did an internship at Jane Street, and I'm starting my PhD in Edinburgh in the fall. And this is joint work with Daan, Leijen, who's also here in the audience and from Microsoft Research. And it's called reference counting with frame-limited reuse. And before I get into the work, I want to say a few brief words about the setting in which this takes place. So while our work is general enough to work also outside of the setting, I think it really shines here. So we start off with the Koka language, which is a strict functional programming language with strong typing. And in particular, it has algebraic effects. And in the first step, we'll compile these algebraic effects away into pure lambda calculus, using the evidence passing style that was introduced last year at ICFP. And then we go from this pure lambda calculus to C code by inserting reference counting instructions according to the Perseus algorithm, which was also introduced last year at PLDI. And a nice thing about these two steps is that none of them need to capture the stack in any way. So in particular, we obtain C code that can just use standard malloc and free. There's no need for any kind of GC or root scanning or anything like this. Now, before I get into our contribution, let me talk a bit about the Perseus algorithm. So Perseus, as I said, was introduced at PLDI by Ranking, Scheer, Demura, and Leijen, and builds on top of earlier work by Ulrich and Demura. And unlike most reference counting implementations, it is not scope-based. Let me show you one example where this differs. So we have a list XS here, and we map over this list, creating a new list, YS, which we then print. And most reference counting implementations, for example, the one listed below, would now drop these two lists at the end of the scope, which in particular means that both lists are live at the same time. They're both in memory while we're printing YS. But the thing is that this is kind of unnecessary because XS is not needed after we've created YS. So we could have deleted XS while constructing YS. And that is what Perseus does. Perseus passes ownership into the map function and into the print function. And this means that now that XS can be deleted while YS is being constructed, which halves the memory usage in this example. So how does this work in the map function? So I'll focus on the first cons branch here. We get a list cell XS, we match on it, and we want to continue using X and XX, its two children. So in the first step, we will have to increment the reference count of the children by inserting the stop instruction. And then we have a drop instruction which gets rid of the cell XS, either by decrementing its reference count or by freeing it if the reference count happens to be 0 after the decrement. And a particularly nice fact about this is that now XS is deleted as soon as possible. So we match on it. We need XS, of course, to be able to match on it, but then we don't need it and we can immediately get rid of it. And with the Perseus algorithm, this is true for all cells. So this is a property called garbage-free. If you can show that the Perseus algorithm is garbage-free, which means that at runtime, all cells will be freed exactly when they are no longer used. And of course, there's a few other nice optimizations which you can do to make this example even more efficient. However, here I want to talk about one particular optimization, and that is reuse analysis. So as you can see here, let's assume that the list XS is unique and comes in with a reference count of 1. Then the drop instruction would decrease the reference count of XS, it would go down to 0, and it would be freed. But immediately after, we will allocate a new cons cell. And this seems kind of wasteful, that we are freeing a cell and then allocating a cell of the same size. So what we can do instead is that we insert this call that we call drop reuse. And what it does is that it looks at XS if it happens to be unique, and if so, it saves the cell as the reuse token R, or it just writes null if XS is not unique. And then the allocation either needs to happen if the reuse token is null, or if the reuse token is actually a cell, we can just write the values in place into the cell that we already have. And it turns out that this can be a surprisingly effective optimization that can often, at least in some benchmarks, make a gigantic difference in performance. However, in this work, we found that it is not quite so simple. And we show several examples how reuse analysis that have, analyses that have been implemented in the past fall short. Take a look at this example, where we have, again, a cell XS that we match on, But now we pass it to a map function, and then we allocate a new console. And what some other previous reuse implementations did is that they would see, we have a console and we want to allocate a console. Let's try to drop reuse XS so that we can use it for the new console. And in a way, this is pretty good because we now have a chance to reuse XS for this new cell. But in a way, it's also not so good because we need to make sure that XS is still live for map. We hold on to it during the call to map. So we insert this stop instruction here. And in particular, that means that the XS we pass down to map will not be unique, and no reuse can take place in this recursive call. And that means that map can no longer update the XS and list in place. So we may have lost quite a lot of reuse opportunities because map can reuse for each cell of the list at the benefit of just having one extra reuse opportunity. And something that's even worse is that now we hold on to XS during this recursive call, which means XS cannot be freed while we construct YS. And now we've again doubled our memory usage from the baseline of the Perseus algorithm because we now have both XS and YS in memory at the same time. We have defined a new reuse analysis called drop-guided reuse, which does not suffer from this problem. And our guiding principle here is that drop-guided reuse analysis should not prevent ownership from being passed. That means, in particular, we want to only reuse dead values. And to achieve this, unlike previous reuse analysis, which usually would insert the drop reuse calls before inserting the reference count instructions, we now insert the drop reuse call after the reference count instruction, after the Perseus algorithm has run. And then it is particularly simple because dead values are exactly the values that will be dropped, and we can just rewrite a drop into a drop reuse when we have a reuse opportunity. In particular, this will avoid the problem from the last slide, and it has both simplified our reuse analysis and made it much less fragile. However, we still had a bit of a problem with this, because the Perseus algorithm, as I've just said, is garbage-free, which means it will never hold onto a cell longer than it needs to be held onto. But this is not true of previous reuse analysis, and it's also not true of our reuse analysis. Because if we take a look at this map function here again, we would normally drop XS. So we would free the cell XS before the recursive call. But now we can rewrite the drop into a drop reuse and hold on to the cell XS potentially as a reuse token R. And we'll hold on to it here at the drop reuse call, then do the recursive call to map, and then use it in the console. So in particular, R will suddenly stay live during this recursive call. And we suddenly have sort of this garbage in memory. However, empirically, we found that this is a pretty good opportunity. Like, this is an optimization you should do. It turns out that this is quite efficient for the map function. So we needed to have a better memory bound to actually be able to precisely say how our automatic analysis here changes the space usage of a program. And we call this new memory bound frame limited. The intuition is as follows. We have a small number of reused cells in each function, which we can treat as a constant overhead. They might be kept alive during a recursive call, as we've just seen in the map example. And so, at least for the map example, our space overhead will be the number of recursive calls that we have times the size of a console. Or in general, it will be frame limited in the sense that it is limited by a constant times the number of stack frames that we have at any given point during the runtime of our program. So how can we actually reason about this? And how can we in particularly prove that our reuse analysis actually is frame limited? To do this, we have simplified the main linear resource calculus of the Perseus work. In particular, we normalized the expressions to make it easier to reason about exactly when an expression is evaluated. And we've been able to introduce just a single star condition, in order to be able to also reason about space usage. So we can now not only reason declaratively about liveness when things go out of scope, but also about exactly the space usage, how much extra space a program will need. I'll give you one example of this calculus so that you get a taste of it. We have here the borrowed environment. These are variables which are not going to be reference counted. And we have a multi-set of owned variables which are reference counted. And in particular, this is a linear environment, which means that if you take a look at the var rule, here we only consume the variable x, so the linear environment can also only consist of x. However, unlike in normal linear logic, we can actually get rid of x out from our context. We can remove it from our context if we insert a specific drop instruction that decrements the reference count. And when we take a look at the let construction, here we can have the star condition to further reason about space usage. So in the let rule, normally in linear logic, what you would do is that you split the context in two parts, into gamma1, which is used to compile E1, the bound expression, and then gamma2 to compile E2. And we can use the star condition to say precisely how the splitting of the context should happen. If we leave it unrestricted, then we'll certainly have a sound calculus. So this calculus will ensure that there will be no use of the free errors, and there will, at the end of the program, all garbage will be cleaned up. So there's no space leaks in that sense. However, we can also introduce the following rule. We can say, if y is a variable in gamma2, it needs to also be in the free variables of E2, which ensures that it will actually be used in E2. And then we can recover the notion of garbage freeness, which was first introduced in the Perseus work, also in this much more simplified calculus. And we can use the following rule, where we say a variable can be in gamma2, either if it's actually used in the expression, or if we can, for example, through a type-based analysis, find out that the size of all of the memory that y can possibly refer to is less than a constant. In particular, reuse tokens are among that. And so we have a syntactic condition that can allow us to actually know what space behavior the program will have at runtime. Now, how do we actually prove that drop-guided reuse is frame-limited? So in a first step, we'll take an expression E that was given by the user and insert the dup and drop instructions, and that will yield a garbage-free program, E prime. Then we do the reuse analysis, which we've also formalized, to turn some drops into drop reuses. And thus we obtain a new expression, E prime prime. However, we can now show that if we have done these two steps, we also obtain a new derivation from E to E prime prime directly in the linear resource calculus using the frame-limited star rule. So this proves that the output of a drop-guided reuse analysis will always be frame-limited relative to the source program. So to conclude, our reuse optimization is not garbage-free. There's a trade-off to be made, and we think it is better to do the trade-off this way. But it is frame-limited, and we show some other examples in the paper. In particular, the previous lean implementation of reuse was not frame-limited. Borrow inference, also introduced by Ulrich and Demura, was not frame-limited. But tail recursion modulo cons is frame-limited in a certain sense, and you can read more in the reference paper. To conclude, I want to give you one last example of how reuse analysis can really shine. In particular, we have defined a new insertion algorithm for red-black trees. And we start off with the following tree type, where we have a color, which is either red or black, a left child, a right child, a key, and a value. And we define a zipper of this tree. We can, of course, turn the zipper back into a tree by using the move-up function. And it just so happens that the zipper has cells which have exactly the same size as the cells of our original tree, which means that reuse analysis can work here to turn the zipper back into the tree, which makes this a very cheap function. In particular, as we ensure that the zipper is always unique, so this reuse can always happen. And now, how do we do the insertion? We do not balance on the way down, where we just record whether we went left or right and use the appropriate zipper to remember this. And again, if the tree that we put in is unique, here again, reuse analysis can work. Then, if we find out that the key is already present in the map, we just move up and reconstruct the tree from the zipper. And else, if the key is not present, we have to balance. And again, in the balancing function, we can reuse the cells of the zipper for the cells of the tree. which means that in the end, this algorithm does not allocate anything if the tree that we put in is unique, except that the one cell that we put in, which holds a new key and a new value. So it really allocates the minimal amount possible. We have one benchmark called the arbitrary benchmark, where we insert 4,200,000 elements into a red-black tree. So Koka here is in red, and the light red is the old reuse analysis. And as you can see, our new drop-guided reuse analysis works quite a bit better here. You also see OCaml in yellow, Haskell, Swift, Java, and C++. And we finally have the new Koka FBIP algorithm that I've just shown you. And it turns out that this is even a bit faster than the standard implementation that Okazaki gives. And it's also a bit faster here than C++. We have more benchmarks, in particular of the deriv benchmark, the n-queens benchmark, a constant folding benchmarks, and the binary trees benchmark from the benchmarks game. And we can see in these benchmarks that our reuse analysis is never worse than the old reuse analysis, and it is competitive against mature systems. Well, thank you, and I'm ready to take questions.
Thank you, Anton.